Now we're getting into optical instruments. So this is about converging lenses. Okay, what is a converging lens? This shape is called convex. And convex means that it bows outward. Concave will mean that it bows inward. So that's convex. It's a convex lens. It's kind of like a magnifying glass. So imagine looking at the side of a magnifying glass. It kind of bows out on either side. That's a convex lens. The outside of your eye is convex. It kind of bends outward. So if it bends like that, it's called a convex lens. And what a convex lens does, what are we doing now? We've talked about light, we've talked about prisms, we've talked about diamonds and how different things we do, and we've gone through critical angle. All of this really has been about refraction and a little bit of internal reflection, but mostly refraction, the bending of light as it goes from one medium to another. As light passes through, it begins to bend. So imagine, let me go over to the prism for a second. If a prism has light that goes in like this, bends a little bit, and then bends again, I can use that same concept to create a magnifying glass or contacts or eyeglasses to take light and begin to bend it and move it, right? Your eye does the same thing. And what a converging lens does by definition, all light rays parallel to the principal axis converge what we're doing now is we're looking at the prism, but kind of more macroscopically. And what I mean by that is when we look at the prism, we're looking at what one ray of light might be doing. But realistically, you've got a lot of light coming in here, right? And with a lens, what's happening is that it's almost like I've got a lot of little triangles, a lot of little prisms. And as the light comes through, what it does is the net effect, what we're looking at now with lenses is the net effect, not just individually the two little bends, but net, like what happens? All rays that enter coming in parallel are going to bend and they're going to converge to a focal on the far side of the lens. Call this F. Principal axis is this guy. The principal axis is an imaginary line. If this is a multiple choice question, the principal axis is an imaginary line that runs right through the middle of the lens. But all these light rays that come in parallel are going to converge to a focal on the far side. So what they're going to do is they're going to bend, and they're going to go right through this focal on the far side. Whoops, getting a little careless with my drawing here. It's okay. So a converging lens, like a magnifying glass, right? So we may have done this with light and tried to make a little dot on the ground or something. All rays that come in parallel to the principal axis converge to a focal on the far side. And there's a focal on the near side, and there's a focal on the far side. Okay. Cool. Converging lenses are really neat. And well, if you're watching this video because you didn't see the lesson in class, when you're back in class, I'll let you hold a converging lens and you can look and see the different images that are created. What's kind of neat, like a magnifying glass, if I hold it up close to the words, the letters look big and right side up. But if I take a magnifying glass, if you have one at home, and hold it at arm's length and look across the room, everything looks upside down and small. So magnifying glasses, these converging convex lenses, can create images that are either right side up and big, or they seem to be able to create images that are upside down and small. In fact, your eyeball creates an upside down, inverted, upside down, smaller, reduced image on the back of your eye because of that convex nature. So you get all rays entering parallel, converge to a focal on the far side, and these convex lenses can create different types of images. So when you begin the ray diagrams front, this is going to help you with ray diagrams front. Ray diagrams front deals with converging lenses. The worksheet that goes with this is ray diagram front. The back will be the diverging. That'll be the next lesson. So what is it saying for this? What we're trying to do in physics at this point, what we're trying to do is imagine what images look like when they're created by these lenses, right? Try to model it. How about that? Maybe the word model is a little bit better. We're trying to model what's happening. So what if I have a lens and I have a focal here and a focal here? And I'm going to give you a little bit of information. I'm going to say the focal length for this is 20 centimeters. That's on either side. And I'm going to say that the distance to the object, DO. DO is object distance. Centimeters are okay here. Kind of nice, right? F is focal length. Okay. We'll add some more to that in just a second. So we're going to put this out here at 60 centimeters. So I'll try to do this to scale a little bit. And my object out here could be anything. It could be a tree. It could be whatever you're looking at. But what I want to try to do is model what that image might look like as it passes through the lens. I can see that when I hold a magnifying glass up, either the image looks upside down and small or right side up and big, depending on where I have it. And there's some other images that are created too. But here's the way we do this. This is called ray diagrams. I'm going to use 3 rays to model where I think my image is going to be. So what 3 rays am I going to use? I know that any ray, I'm going to start at the top of the object, any ray parallel to the principal axis will converge through the focal on the far side. We're going to kind of model how microscopes work, telescopes work. I also know that any ray that passes right through the middle of the lens, like right through the middle, in any direction, right through the middle is going to go through undeflected. So that's kind of cool. Like if I have a lens like this, any ray through the middle doesn't bend at all. Really cool. So if I take a straight edge and I go from the top of my little tree here, straight through, there it goes. And my third ray is a reversal of the first. If I go through the near focal and come out parallel, so those 3 rays, parallel through the focal, far focal, right through the middle of the lens, through the near focal, come out parallel, and guess what? Where they come together is where that image is going to be. So my tree looks upside down and small. Well, that's exactly what's happening when I look through a converging lens at an object that's pretty far outside the focal. I get an upside down small image. The question is, where is the image? The distance to the image, what is that? What is the magnification? How big or small is it? So now what we're looking at is basically, again, we're looking at refraction kind of more macroscopically and just trying to figure out, okay, if this light is passing through a lens, what does the image look like? What are we getting? The magnification, distance to the image. So we need a new equation. So introduced here is the thin lens formula. And the thin lens formula says that 1 over F equals 1 over DO plus 1 over DI. I can leave it in centimeters, meaning 1 over 10, 20 is my focal, 20, 1 over 60 plus 1 over DI. And when I do this, I get 1 divided by 20 minus 1 divided by 60, 1 over that answer, 1 divided by the answer, and I get 30 centimeters. Which means my image distance is about 30 centimeters on the other side of the lens. Hey guys, guess what? Even with a pretty silly diagram, this being 20 centimeters, all measurements made from the lens itself, if that's 20 to the focal, 30 centimeters, yeah, that's about right. That's about 30 centimeters to that point. right? It's just outside the focal. So I can handle that. And that got a little messy, but you can kind of see what I just did there. You can always go back in the video if you need to clean it up. But yeah, 30 centimeters works. Now, my magnification, I need another equation for that too. So this is the thin lens formula. 1 over the focal length equals 1 over the object distance to 1 over the plus 1 over the image distance. My magnification equation is negative DI over DO. Okay, so my DI was 60, so, excuse me, 30. Goodness, 30 over DO, that was 60. So negative 0.5. Fantastic, no units there. My magnification equals negative 0.5. Now, does that make sense? Well, in physics, the negative simply means that it's upside down. Not that it's smaller, but that it's upside down. The 0.5 means that it's smaller. If I get a magnification of positive 3, the image is upright and 3 times bigger, like the zoom on a scope. If I get a magnification of negative 0.5, negative means upside down, 0.5 means smaller. So, for instance, if the original height of the object, let's say at HO, was 40 centimeters, what if the height of the object was 40 centimeters? That'd be the height of this thing. How tall does it look to me? What's the height of the image? Well, it's just the mag times the height of the object, which would be negative 0.5 times 40, or 20 centimeters. And we're actually going to say inverted for that negative. Okay, cool. So that's how to do ray diagrams for convex converging lenses, okay? If you get a little bit closer, to the focal length, that lens is pretty rough, isn't it? What do? You might see this on your diagram. You might see it look like this. I might even replace the lens with just a line, because it's really all I need, right? All I need is a line to know where it's bending. So what if it looked like this? My first ray goes parallel through the far focal. My second ray goes right through the middle. My third ray goes through the near focal, comes out parallel, woo, and it should come together right over here if I've drawn it well. Cool. That's converging lenses, the thin lens formula, and the magnification. Hope you have a great day.